The music was still playing, but the dancing had stopped. 2 suspended walkways had just torn loose. They fell onto the crowd below. Roughly 1,600 people had come to celebrate that night. It was a Friday night tea dance. Some danced on the floor. Others stood on the walkways above, watching. 114 people were killed. More than 200 were injured. But this wasn't a failure of steel. It wasn't a failure of welds or construction. The walkways had already been doomed months earlier. They were doomed before the hotel even opened. A single change had been made to a drawing. That change was never properly checked. The Hyatt Regency Kansas City opened in 1980. It was immediately celebrated for its dramatic atrium. The atrium was a soaring interior space. Suspended walkways crossed at the 2nd, 3rd, and 4th floors. The walkways were the architectural signature of the building. Guests loved standing on them to look down into the lobby. On Friday evenings, the hotel hosted tea dances in the atrium. July 17, 1981 was one of those nights. The walkways were hung from the ceiling by vertical steel rods. In the original design, each rod was continuous. One long rod ran from the ceiling all the way down. It continued to the 2nd floor walkway. The 4th floor walkway hung from the same rod at the midpoint. A nut and washer at each box beam held the system in place. During construction, the steel fabricator ran into a practical problem. Threading one very long rod through multiple floors was difficult. It was also slow and required precise alignment. Haven Steel proposed a simpler solution. They suggested splitting the rod into 2 shorter ones. The upper rod would run from the ceiling to the 4th floor walkway. A second rod would run from the 4th floor walkway down to the 2nd floor. On paper, it looked like a minor adjustment. It seemed like a reasonable way to speed up installation. In reality, the change was catastrophic. Here is why the change mattered. In the original design, the nut and washer at the 4th floor box beam only carried the weight of the 4th floor walkway. The 2nd floor walkway hung from its own section of the continuous rod below. The loads were distributed along the full length of the rod. In the modified design, the upper rod now ended at the 4th floor box beam. The entire load of the 2nd floor walkway transferred upward. It moved through the lower rod. That load concentrated directly into the 4th floor connection. One connection now supported 2 walkways. The load on the 4th floor box beam connection doubled. The 4th floor box beams were not simple steel sections. They were built from 2 steel C-channels. The channels were placed toe to toe. They were welded together along their edges. The result was a hollow rectangular section. A seam ran down the middle of the beam. That seam became the critical weak point. Under the doubled load, the nut and washer began pulling upward. They pulled through the bottom of the beam. The weld between the 2 C-channels started to split open. The split grew along the length of the seam. The nut and washer eventually pulled through the gap. It was like a button being forced through a buttonhole. The buttonhole was never designed to open. Once the first connection failed, the load shifted instantly. It transferred to the remaining connections. Those connections failed in rapid sequence. The 4th floor walkway fell first. The 2nd floor walkway was still attached to it. Both walkways came down together onto the atrium floor. The connection had been marginal from the beginning. Even the original design provided only about 60% of the required capacity. That capacity was measured against the Kansas City Building Code. The modified design carried double the load on the same connection. Its effective capacity dropped to roughly 30% of what was required. The connection was never close to adequate, and no one caught the problem during review. GCE International was the engineering firm of record. Jack D. Gillum and Daniel M. Duncan were the principals. Haven Steel submitted the revised shop drawings. The drawings clearly showed the two-rod configuration. Those drawings went to GCE for review. The review was approved. The stamp of a licensed engineer went on the drawings. No structural reanalysis of the modified connection was performed. The load implications of the change were never calculated. This is the part engineers still study to today. A shop drawing review is not a formality. It is not a procedural checkbox. It is the moment when a licensed engineer must ask one critical question. Does this change affect the loads? That question was never properly answered. Or, if it was asked, no calculations were ever done. Either way, the stamp went on the drawing. The post-collapse investigation was led by the National Bureau of Standards. Their technical analysis was exhaustive. Their conclusion was clear and unambiguous. The collapse was caused by the load transfer from the two-rod modification. The fourth-floor box beam connections were fundamentally inadequate. They could not carry the loads they were required to support. The modification had never been subjected to proper engineering review. The professional consequences were severe. The Missouri Board of Architects, professional engineers, and land surveyors conducted formal proceedings. Jack D. Gillum lost his engineering license. Daniel M. Duncan lost his engineering license. GCE International lost its certificate of authority to practice engineering in Missouri. The board's findings were explicit. They cited gross negligence. They cited misconduct. They cited unprofessional conduct in the practice of engineering. But the deeper lesson is not just about the individuals involved. It is about the system that is supposed to catch these errors. Shop drawings move through a defined chain. The chain runs from fabricator to engineer of record. It continues from engineer of record to stamped approval. It ends with stamped approval, moving into actual construction. At every link in that chain, someone must ask the same question. Does this change affect the loads? When one link stops asking that question, the entire chain breaks. The Hyatt Regency collapse changed how the profession treats shop drawing review. It became standard doctrine that a change detail is not minor. A change detail must be proven safe through analysis. Engineering ethics programs still use this case as a core example. It teaches professional responsibility and the duty to verify changes. On the evening of July 17, 1981, the atrium was full of music and people. By 7:05 p.m., it had become a collapse site. Investigators later determined that the fourth-floor connection had been overloaded. It had been carrying loads it was never capable of handling. This was true not just on the night of the collapse. It had been true every day since the building opened. The failure wasn't sudden or unexpected in hindsight. It had been building in increments since the first person stepped onto that walkway. The walkways didn't fall on July 17, 1981. They fell the day someone approved a drawing without doing the math. The night in Kansas City was simply when the accounting came due. Every engineered system carries the same underlying risk. The risk is not usually sudden catastrophe. The real risk is a small decision made quickly and reviewed carelessly. That small decision can reshape everything downstream. The stamp on the drawing is supposed to be the last line of defense. In Kansas City, that line of defense failed. The consequences of that failure are still studied today.